So I've got the breakout board all connected up to Mach 3 now. I've already configured the ports and pins on it. So I've got it hooked up to my 1.8 kilowatt servo driver. I don't have all the drives connected up, but so I can't show you the safety system all communicating and talking to each other. But I can show you some of the waveforms on the oscilloscope, and I can show you the charge pump circuit and how that works, and maybe the multi-vibrator outputs to show them extending the pulse form coming in. So I've got this relay over here, which is part of my charge pump system. So when a 12.5 kilohertz signal comes through, it activates or it triggers the retriggerable monostable multi-vibrator over here, which is that chip there. So any signal that's above 12 kilohertz triggers that, and thus triggers that relay there. So at the moment Mach 3 is all loaded up and it's outputting this signal. So if I were to close Mach 3, you'll probably see that relay just trigger. So Mach 3 is off and you saw that relay trigger. If I turn it back on again, the system's active. I've also wired the enable signal for each of the drives, so if I hit reset, I can turn that off and in turn turn it back on when I actually reset the system itself. The charge pump system itself can't really be dependable as a safety system simply because it's controlled through software. So say if your software crashes, there's still a chance that I can send out a 12.5 kilohertz sample or signal, and then that there won't turn off. So your drives are still powered on. So the intention of the safety system is to control all of that in hardware. So what I've done is I've configured all the inputs and all the outputs of the servo drivers and some of the designated outputs and inputs on the board. So if any one of them trigger, it will trigger the respective outputs. So it would either put all the drives into an error state mode, or if the user wanted to, you can configure the outputs to trigger an auxiliary relay or maybe your main contactor, and in turn shut all the power off to the whole system. So in my instance, I'm probably just going to use the charge pump over here. I'm going to use the charge pump, and that's going to trigger the main contactor and send power to all my servo drives. I'm then going to use the input or an e-stop coming through over here to control my safety system. So if the e-stop is hit, all of the drives go into an emergency stop mode, but it doesn't necessarily cut all the power. Nevertheless, all of that is controlled in hardware. So I've got the oscilloscope set up to the output pins. There's some ringing on my oscilloscope over here, but it's a bit annoying because I think it's just the way I've configured it. If I actually output or take the output off and connect to ground, the ringing actually is still prevalent. So it's a bit annoying, but I think I just need to learn how to use the oscilloscope properly. So yeah, if I actually fast forward, or if I move some of the axes forward, you can see that the output pulse is shown on the actual oscilloscope itself. So I'm going to go ahead and take a sample, and then I'm going to zoom in for you. So before I used a 3 amp MOSFET, so I've used a 3 amp MOSFET on my outputs, still in open collector mode, but what I did see was because of the gate charge on the MOSFET, there was quite a skew on the output. So effectively, if I scroll to the right, just change the scale quickly, make this a little bit easier. So over here you can see there's a sharp drop off. There's a sharp drop off on my oscilloscope, but before I actually had quite a rounded drop off, and I think that's simply because the gate on the MOSFET is a capacitor, and with a higher gate charge it just made a larger RC filter effectively. So that actually was so prevalent on my previous setup that it took up a proportion of the waveform at a higher frequency. So I've eliminated that problem, but in turn what I've done is I've minimized the amperage of the actual MOSFETs. So these are 380 milliamp MOSFETs, but they've got a gate charge of about 0.2 nanocoulombs opposed to the 7.4 nanocoulombs that are otherwise used on the 3 amp MOSFET. You can see that actually there's an offset, so that the channel 1, so the actual yellow line up here, that's my input. That's actually output from the motion controller. And then the second channel over here is my opto-isolated output. So there is a delay, but the delay in the grand scheme of things is absolutely tiny. So I'm going to zoom in to the front. So if I zoom in, I measured this earlier and it was about 16 nanoseconds. So let's zoom in. So I've got my cursors set up. The cursors are not strictly set up correctly because actually you're triggered the moment you go over your threshold voltage. So for that to actually work, I probably should set it at the threshold voltage, and then you can see this has got a tail off at the beginning. So set that at the right threshold voltage and actually get the time off that. But you can pick up the delta on the time is 66 nanoseconds. So in the grand scheme of things, it's quite small. Of course, you want everything, all your outputs on all your respective drives to be configured so they have the same timing, otherwise each of your drives would otherwise not be synced up. But 66 nanoseconds is very, very small in the grand scheme of things. So when you work it out, it's, well, if your drive, if an output pin is connected directly to your motion controller, which it shouldn't be, then you're not off by much anyway. You're pretty well synced up. But in this instance, your outputs have the same delay, if that makes sense. So you're otherwise synced up anyway. Another thing that's actually quite interesting is if I zoom in a little bit, you can see that, or you can see some ringing on the output pin of the motion controller. So I don't know why that is, probably the way that it outputs a signal, but there is no ringing on the output of the opto-isolated output, so that's good. The tail off as well is relatively good as well. That's quite solid. Make sure you zoom in there as well. So yeah, so you can see some slight ringing again on the motion controller output, but then the opto-isolator seems to pull that down quite nicely. So there's less ringing there. So all in all, the signal integrity is actually, it's okay, it's good. So my previous setup was actually done at 100 kilohertz, so I had the kernel speed set to 100 kilohertz, but I'll just show you at 400 kilohertz, running at effectively its maximum kernel speed. So if I just stop that there and I zoom in, the effects are ultimately the same. So you can see that the cursors are set and the delay, or the difference in time, is about 66 nanoseconds. There still is the ringing effect prevalent, and there is the skew on the actual output on the optocoupler. But the drop off is also very similar in that magnitude. So if I zoom in over here, you can see they look relatively identical to the previous video, or the previous clip that I showed you at 100 kilohertz. So I've got the oscilloscope hooked up to the monostable multivibrator output. The output in this case is 5 volt TTL voltage levels. So I've got the kernel speed set to 400 kilohertz, and the whole idea of using the circuit or this setup is so I can interface, say, a slower operating stepper motor, which can only see a pulse duration of a certain length. So for example, if you've got a kernel speed set to 400 kilohertz, your actual pulse width only exists for a certain period of time. And that makes sense because if it was any longer, then it will interfere with the next corresponding pulse. So, but if you're running something when which you only need, say, 1000 RPM, when which that's going to result in each of your pulses being spaced out by a certain amount. So in this instance, I'm running at a significantly lower RPM simply because the stepper motors can't run at a faster RPM. So what's going to happen in this instance is the signal is going to be generated. The stepper motor is not going to be able to see the pulse simply because it exists for a short period of time, and optocouplers and the stepper motor are not good enough to pick up on that, and it does nothing. But if you were to extend that pulse, any more longer, you could get the stepper motor to pick up on that pulse, and that pulse doesn't interfere or correspond or conflict with the next pulse. So you can thus run a higher kernel speed. So you can run your servo drivers, in my instance, at a fast speed, 3000 RPM, and you can also run a much slower system. So in my case, the stepper motors are running at a slower speed, and therefore they can actually see the pulse rather than do nothing. So I've got it all set up at the moment. If I click run, you can see that I've got my pulses streaming in. They're streaming in at a kernel speed of 400 kilohertz, and then I've got my output. So if I actually probe my output or come in with my output with my cursors, you can see the pulse duration, or you can see how much I've extended the pulse by. So you can see my actual input pulse is coming in at 1.25 microseconds. So I'm going to just zoom in there so you can have a look. Just about probably make it out, but it's about 1.25 microseconds, or 1.26 in this instance, which corresponds, so it's 1.26 times it by 2, because you'd otherwise have 2 pulses, and then 1 divided by that, which is 400 kilohertz. And then if you actually measure the output pulse, or the output duration of the monostable multivibrate output, it's supposed to be about 6.5, so it's reading about 6.54, and that corresponds to a frequency, or a total frequency, or max output frequency of around 76 kilohertz, I think. So that's fine for my application. My stepper motors can't even run at a higher speed than that. I mean, they can with micro stepping and whatnot, but effectively the optocouplers on the stepper motors cut out at about 100 kilohertz. So yeah, the circuit works quite well, and it enables me to run a high kernel speed for all my other servo motors, and then thus use my stepper motors as well on my Z axis. So taking a sample, and then we can actually have a look at the time delay between the actual input coming through and the monostable multivibrator. So this will help us with synchronization. So as before, we measured it to be about 66 nanoseconds. We'll come in here and have a look. I haven't actually measured this off camera, so this would be interesting because it could be really crap. But yeah, so I'll put that there. Again, as before, I should really put it at the threshold, but we'll put it at the start of the waveform just to get an idea of what it is. So it's coming in and it's reading about 80 nanoseconds. So again, in the grand scheme of things, the delay is quite small. So yeah, so the actual output, so the open collector outputs, we measured them at about 66 nanoseconds, I think those were there, and this is 80 nanoseconds. So they're in a similar range of magnitude. I've actually done the differential outputs as well, so the differential outputs are run to the servo motor, and they're also in a similar magnitude. So everything should be relatively synced up, or good enough for my application anyway. So that's pretty much it from me. I'm going to go ahead and put this in an electrical cabinet now. So I'm going to disconnect it up from this test setup and put it in there. But if anyone's actually interested in purchasing one, or if anyone's actually interested in having an application in which they can use it, then let me know. I might put a poll down below just to get a gauge. If anyone is interested, I can go ahead and make a couple of these and post them on so someone else can buy them. Quite a lot of work has gone into designing this, and that's simply because I needed the board to function a certain ways to actually get my application to work. But I understand some other people might have similar applications out there. You may well be able to use it in yours. I think the beauty about using something like this is it enables you to use the cheap servo drivers, which would otherwise be better than your stepper motor equivalents, and it will be plug and play. It's just a case that that's all configured. The ports and pins is something that you need to configure with Mac 3, but it's just a case of plugging that in, plugging in your servo drivers using the DB25 cable, and then you're off and ready. So there's not a lot you need to do. I've configured the board so I've got these slow optocouplers, and then if it is the case in which people are interested, or you are interested in buying one, then I'd probably look to replace all the slow optocouplers with much faster optocouplers. I'll still probably keep the option of running a 5-volt system. So some of these are configured for 5 volt and some of them are configured for 24, so I'll probably have that all set up there. I also have some of the jumper pins at the back, so I'll show you that. I'll disconnect the board. I should probably take that off there. So the jumper pins on the back at the moment are just solderable jumper pins. So they're the case in which they're effectively there to control the safety inputs and outputs. So the safety system all relies on these jumpers being configured in a certain way. But I may well put some hard jumpers in there rather than solderable jumpers, so just some pins sticking out on the board in which the user can come along and jump the correct terminals. But in essence, you need to jump some of these terminals to configure the inputs and outputs on the safety system, and also choose whether you want any of your servo drivers connected up to that system. So and then your e-stop comes in there and triggers all of that. But otherwise, I think everything else on this board functions as intended. So if anyone is interested and you do want to purchase a board, or maybe you have an application which is similar, then let me know down in the comments. Maybe fill out the poll, and then I can have an idea of whether, I'll go ahead and make some of these.